Welcome to Brain Vision.
So we need to find the final temperature of the system as well as the amount of water, steam, and ice that are present. So here we know that T initial equals 0 degrees Celsius. Rather, let's not make that assumption just yet. However, for part A, in order to find the final temperature, we at least know that the net heat of the system equals 0 joules. This is an isolated system, so it's not. So we can say that if this is an isolated system, we can say that the heat from the steam plus the heat from the ice plus the heat from the can will all equal 0 joules. And more specifically, it's going to be that the steam is providing the energy and the ice and the can are gaining energy from the steam. So in this case, we can say that let's first specify that this is going to be a copper can. So when we use the specific heat, we're going to have to use the specific heat of copper. So we can say that 0.446 kilograms times 390 joules per kilogram per degree Kelvin times T. So this would be the essentially be the heat from the can, because the initial temperature of the can is going to be 0 degrees Celsius. So we can simply say T minus 0 degrees Celsius is of course just T. So the final temperature T, we know that the can is gaining heat from the steam. The ice will be gaining heat from the steam. So we can say that this is going to be plus 0.095 kilograms. This would be the essentially the weight of the ice, and we're gonna have to multiply this by the specific heat times the change in temperature as well as the latent heat of formation in order to see if it actually all melts into water. So we can just say that 0.095 kilograms, and then we can say times, I'll write it down here, 3.34 times 10 to the 5th joules per kilogram. So that would be the latent heat of formation for water, plus 4,190 joules per kilogram per Kelvin. And again, the ice starts at T at 0 degrees Celsius, so we can just say times T and close it off. And for the last term, we have the heat from the steam. So it would be plus 0.035 kilograms times 2,256 times 10 to the 3rd joules per kilogram. This is the latent heat of vaporization. Plus, and then here it would be again the specific heat of water, so 4,190 joules per kilogram. We're assuming that everything melts and everything condenses as well. However, here it's not going to be T. The steam actually begins at 100 degrees Celsius, so we'll have T minus 100 degrees Celsius. And again, this is all going to be equal to 0 joules. And so we can actually plug this into a solve function in your TI-84, 85, or 89. Of course, you can just simply lose all of the units and include T, and you'll basically be solving for T. And when you do this, T is going to be equal to 86.1 degrees Celsius. Now, this is in between the temperature, in between the melting temperature and boiling temperature for water, which means that in this system, all of the steam condensed and all of the ice melted, because if the final temperature is 86.1 degrees, steam nor ice can exist. So for part B, when it's asking how much steam, ice, and water are present, well, we can say no steam nor ice present. And then the mass of water, due to the law of conservation of mass, would simply be the mass of the ice initially plus the mass of the steam initially. And this is giving us 0.130 kilograms. So this would be the mass of the water present after the system reaches equilibrium. That is the end of the solution. Thank you for watching.